Hello everyone and welcome. In this video, I'm going to teach you how to model and simulate your robotic arm using Simulink&Simscape Multibody. We'll start with the basics of the simulation and modeling, which can be considered as an introduction. This step will cover the essentials, some solver configuration advices, and some basic tricks. Then, we will continue on 3D modeling of the robotic arm, including the rigid bodies and transformations, different types of joints, actuator models, and controllers. And finally, we will move on to the last part, where you will basically learn how to simulate your robotic arm for a certain time interval. So, let's start with the basics. Once you have opened a blank model on Simulink, there are three essential blocks you should use. First one is solver configuration, which defines solver settings to use for simulation. Simulink won't be able to solve the system without this block, obviously. The next one is mechanism configuration. This block sets mechanical and simulation parameters that apply to an entire machine. Simply put, this block will determine the environmental effects that apply on your robotic arm, such as gravitational properties, or the parameters that will be used to compute numerical partial derivations, etc. The third one is the world frame. World frame is basically the ground of all frame networks in a mechanical model. This will provide our system a unique motionless frame, which will be very useful in simulation process, since we construct our system on a global reference point. Also, you can use more than one world frame block, but all will represent the same frame. So, you can think of it as if it is a ground for an electrical model. Okay, now you see the robotic arm model. First thing I want to mention that I would strongly recommend you to use subsystems. This will help you to organize your model in a better way, and it is so easy to create one. You simply select some of the blocks, and then under the diagram section, you just click on the create subsystem from selection, and it is just easy as that. Let me reverse this. Let me explain it to you using joint 1 subsystem. Those blocks together represents a single joint on the robotic arm, and all those tiny pieces assembles one part of the whole system. So, creating a joint as a subsystem and then think of it as one when you assemble the robotic arm will become handy in later. By this way, you can rearrange the joint 1 and put it wherever you want on the robotic arm as whole, and you can then will be able to, let's say, fine-tune it if it's required, instead of leaving all parts separately in the whole model. Also, it is easier to establish an orientation in the system with this simplicity on look. I personally feel myself more comfortable while working on an organized system. The other thing is that you should reparameterize your model configurations for your solver expectations. In the configuration parameters section, you can see simulation time options, solver selection options, and solver details, etc. You can set the time interval for your simulation. Let's say we want it 4 seconds, and it's just easy as that. The main thing is that if you want to solve the differentials in a specific way, you can set it for your preference, or if the tolerances and the step size is important to you, you can adjust it as well. I do not recommend to modify these options if you do not know what you're doing, because it will greatly affect your computer performance. But in a brief explanation, I'm using variable step in order to have more flexible modeling, and OD23 stiff trapezoidal solver for more accurate differentiation and integration operations in solving process, and relatively low maximum step size in order to increase the solver sampling, or let's say quantization. Okay, with those setups, we can move on to modeling. In order to model a robotic arm in rigid body, obviously, you should create them first. To create rigid bodies, there are several ways to follow. Once you add a solid block onto your model, double-click on it, like this. And the options window will pop up. In the properties section, you will see geometry, inertia, graphics, and frames. In the geometry option, you define the geometrical features of your solid. Simulink gives you basic shapes like brick, cylinder, sphere, ellipsoid, etc. These are basic shapes, as I mentioned, and you can select, for instance, ellipsoid and define the radii on each axis, and of course the unit of the measurement. And then just click on the update visualization button and you will see the solid that you created. But since we are working on more specific model, we need more detailed solids. Now I want to mention revolution option. Here you can see, once you select the revolution, it comes with a cross-sectional array with full extent of revolution as default. Let's check out on base cover solid of our model. Here you can see it is created by revolution with a specific cross-section array. In order to create a solid like this, there are some easy steps to follow. You can simply create your own array in MATLAB and print it on a figure with a code of 2 lines. It could become more, but basic idea behind it is still easy to apply. If you run the code, you will see the cross-sectional area of the solid. Now, with a little bit help of our imagination, revolute this area around the y-axis and you formed an object, right? This is kind of what Simulink does for you. It revolutes the cross-sectional area around y-axis and creates an object for you. This is a very easy way to create the solid parts of the system. Yet again, we are working on a very specific model with full or more detailed uneven shapes. So this method will eventually fail to help us to create the whole system. So what should we do then? What we are going to do is create those models with the help of the CAD design softwares. Then import those files as either STL or step as in STEP type. Now I want to mention that I would prefer to use step files since it is easier to work on. But the main difference between working with a step type and STL type is inertia options. For step files, Simulink can calculate the inertia from geometry, as you can see, and all you have to do is simply put the density or the mass of the object. But if you are working with STL files, inertial parameters become more specific or complex, I would say. Let's create a new solid from STL file. Okay. We put solid block onto our model as before and double click on it and simply select the from file option and file type as STL, and then you should type the address of the file where you contain it, or you can open it with the file explorer. Let's choose this one. The thing is, as you can see, nothing is showing at the right hand side of the window. This is because rotational and translational transforms for these types of files stored in the file data which is the exact case why I don't like them, because it feels like you cannot put it where you want it on the system. It has many advantages though, since all parts comes together with each other easily. But as I mentioned, Simulink usually cannot solve the inertia from geometry, since the word frame and the data from the STL type will probably have conflicts. For instance, center of the mass cannot be evaluated, or principal axis of the solid cannot be evaluated as shown. But to overcome this problem, you should customize the inertia by hand. You just select custom type, and you have to reparameterize these arrays. And when you do, you can finally see your parts. Actually, it is not a big deal though, since you can look up the table on the CAD software and get those information easily. Yet again, I just prefer to work on the step type. Okay. Let me erase this. To continue, after you have imported all the files of your solid blocks, I mean in this case, I have imported base, imported RX28, ARM parts, another ARM part, and etc. There are mainly two things to do. First, you should create the rotational and translational transformation blocks in order to put the blocks and joints to the exact points on the working place where they should be placed. Let's check out on our model. Okay, finally it is compiled, and if we take a close look on our model, you can see the robotic arm. Okay. Yeah. As you can see, all the joints and relative parts gathered under a specific subsystem, and they are positioned precisely with rigid transform blocks. Here I can visualize it for you. Transfer functions for those parts, transfer functions again, transfer functions again, and another. Those parts are positioned precisely with a rigid transform blocks. Let's see what happens if we don't use them. We go back to our model, and I'm gonna simply erase some of these and reconnect them without. Okay, let's run the simulation again and see what happens. Okay. As you can see, they are all around the place, and this situation would prevent our simulation to be accurate. So basically, transformations are essential in robotic systems and very essential in this project. If we turn back to changes and have a look at this rigid transform, as you can see, one rigid transform block basically defines a fixed 3D translation between two frames. You should exactly know the structure of the robot to set them properly though. Also, these values here can be used to create matrices for translational transformations at starting state. If we turn back to our model. Okay, let's continue. In the last part of the video, I want to show you the actuation, how to simulate the excitation or drive of the robotic arm. To do this, you need several joint blocks. In the Simulink library browser, you can find several types of joints under Simscape Multibody sections. Since our robotic arm uses 4 high-torque servo motors, I'm going to use revolute joints on this project to represent the rotor parts. If we take a look at the joint 2 subsystem, for instance, you can see 4 connections on the ports of the joint block. 2 of them are used for translational operations and as in the description of the block. It represents a revolute joint acting between 2 frames. It gives 1 degree of freedom to our robotic arm as it provides a rotational structure for the follower frame around z-axis of the base frame. The other 2 ports are basically the same, but one is input of the motion while the other is the output of the motion. If we take a look at the revolute joint block again, for actuation considerations, I have selected torque to be automatically computed while I'm giving the motion excitations as input to the system. And in the sensing, I have selected position only, but one can select velocity, acceleration, or actuator torque. The main thing I want to mention here is that we are simulating a physical object, not something on the Simulink scope. In other words, the signal we are using to excite the servo motors here is not a physical object actually. Therefore, we need to use a Simulink to PS converter at the input side or vice versa. Speaking of signals, the signal builder block here represents the controller output of the servo motor. For the exact simulations, one can construct a closed loop or open loop system of a servo motor and then take the output of the signal as input. But in this video, we're just gonna imitate the system with the signal builder block. Let's have a look on this. Okay. As you can see, this signal builder contains a specific signal for the simulation. It represents the position in degrees versus time, like at node 1. It starts to move from 0 degrees to 30 degrees and remains still until 4th second and then returns back to 0. I should mention that Simulink assumes rotational position inputs in radians, so you have to convert degrees to radians with a gain block or simply scale the signal in radians in the first place. If we take a look on the scope, as you can see, the position output is mirrored in x-axis because we used minus sign in the gain block, and it is very important to consider since it will affect the direction of the rotation. And finally, you just hit the run button in the middle of the toolbox to run and simulate the system and observe the behavior of your robotic arm. I hope this video will help you on your projects and have a good day.